In this section, we'll learn about various sorting algorithms. As we know, sorting is a process in which data is arranged in some specific order. For example, if we have these numbers, then sorting them in ascending order gives us this result. Sorting them in descending order gives us this result. Here we have sorted numbers, and sorting can be performed on other type of data also, like strings or records. And in most applications, generally a list of records is sorted, and the sorting is done based on a key value, where that key value is a part of the record. For example, if we have this list of records and we sort these records based on name as a key value, then the result is this. All the records are arranged such that the names are in ascending order. Now, if we perform sorting on age, then the result is this. All the records are arranged such that age is in ascending order. Now, if we perform sorting based on salary as key value in descending order, then the result is this. You can see all the records are arranged such that salary is in descending order. Now, in our algorithms and examples, we'll perform sorting on a list of integer values only so that we can easily understand the logic of the algorithm. Now, let's talk about the importance of sorting. Keeping the data in sorted order helps in faster information retrieval. For example, take the case of a dictionary or a telephone directory. Since all the names are arranged in sorted order, we can easily look for a word or a name in the dictionary or a directory. If the words were not arranged in sorted order, it would be very difficult to find a word in the dictionary. Similarly, in computer applications, information retrieval is faster and more efficient if data is stored in sorted order. We'll study different sorting algorithms, and in all algorithms, we'll have multiple passes. We can think of a pass as a step in sorting, and after each pass, the data becomes more and more sorted, and after the last pass, the data becomes totally sorted. And depending upon the algorithm, there can be many comparisons and exchanges that have to be performed in a pass. Now let us see the difference between sorting methods that are in place and sorting methods that are not in place. Now, sorting methods that are in place don't need any extra storage for performing the sorting, while sorting methods that are not in place need some extra storage for performing the sorting. And this extra storage is generally proportional to the size of data. For example, in merge sort, if we have to sort an array of n integers, then we need an extra array of n integers. In sorting methods that are in place, we might need some constant number of variables. That number is independent of the size of data, and that extra storage can be neglected. For example, these are all in place sorts, and we need only one extra variable to perform the sorting. Now, the sorting methods that are in place are also known as minimal storage sorting methods. So if the size of data that is to be sorted is very large, it is better to use an in-place sort, because if we use these sorts, then a lot of extra storage will be required. Now let's talk about sort efficiency. There are different sorting algorithms and they are compared basically on these two parameters. First is the space required for the sorting, and second is the time taken to perform the sorting. This one we have already discussed, and we have seen that it is better to use an in-place sort if the amount of data to be sorted is very large. Let's come to this one. Now there are two basic operations in sorting: comparisons and record movements. These record movements are generally a constant factor of comparisons. So we can say that the main operations are comparisons. So the runtime can be measured by counting the number of comparisons. More comparisons would mean more runtime, less comparisons, less runtime. Now counting the exact number of comparisons is always not possible. So an approximation is given by O notation. So the runtime efficiency can be expressed in terms of O notation. Some sorting methods are data sensitive. That is, the runtime depends on the initial order of the elements. And these sorting methods have to be analyzed in three different cases: when the input data is in sorted order, when the input data is in random order, and when the input data is in reverse sorted order. In this video, we'll talk about sort stability. Now, data to be sorted can have duplicate elements, and a stable sorting algorithm will maintain the relative order of these duplicate elements, while an unstable sorting algorithm might change the relative order of duplicate elements. Now, suppose we have to sort these records based on name. We can see we have 3 duplicate records. This is the output given by a stable sort, and this is the output given by an unstable sorting algorithm. We can see that in this output, the relative order of these duplicate elements has not changed, 32, 67 and 12, 32, 67 and 12. While in this output, the relative order of these duplicate elements has changed. Here it was 32, 67, 12. Here it is 67, 12 and 32. So a stable sorting algorithm preserves the relative order of the duplicate keys in the sorted output. If records Rx and Ry have equal sort keys and Rx precedes Ry in the input data, then in a stable sort, Rx will precede Ry in the sorted output data also, while in an unstable sort, Rx and Ry can be in any order. Now, stable sort is desirable in cases when records sorted on one key are again sorted on another key. Let's see an example. This is a list sorted on name. All the names are in ascending order. Now we'll again sort this list based on grade. This is the output given by an unstable sort, and this is the output given by a stable sort. In both the outputs, grades are in ascending order. In this output, the names of all students in a grade are in alphabetical order. But in this output, the names of students in a grade are not in alphabetical order, because this unstable sort changes the relative order of duplicate elements. Suppose these duplicate elements are 3, 3, 3. So here the order was Ankur 3, Mansi 3 and Shreya 3. Here the order has changed, but here the order has been preserved. So here the names of students in a grade are in alphabetical order. In this video, we are going to discuss the selection sort algorithm. Now, in selection sort, sorting is performed by selecting the smallest element in each step and placing it at its proper place. For example, suppose you are given these numbers and asked to write them in ascending order. The most natural way anybody would do this would be to select the smallest number and write it here. Select the smallest from the remaining, right here. Select the smallest from this remaining, right here, and so on. So this is the simple idea on which selection sort is based, selecting the smallest element in each step and placing it at its proper place. Now let's see the whole procedure for the selection sort algorithm. This is the array A of n elements that we are going to sort in ascending order. Now in pass 1, first we'll find the smallest element from this whole array, and the proper place for that element would be this 0th position. So we'll swap it with A0. In pass 2, we'll find the smallest element from this portion A1 to AN minus 1 and swap it with A1, because the proper place for that element would be this. Now in pass 3, we'll find the smallest element from this portion and swap it with element A2. And this process will continue. And in the last pass, which will be n minus 1th pass, we'll find the smallest element from these two and swap it with element AN minus 2. So after n minus 1 passes, this portion of array has become sorted, and this element will obviously be the largest element left. So we can say that the whole array has become sorted after n minus 1 passes. Now let's take an example and see how selection sort works. This is an array of 6 elements, and we are going to sort it in ascending order using selection sort. Now in pass 1, we'll select the smallest element from the whole array and swap it with A0. So 12 will be swapped with 45. Now in pass 2, we'll select the smallest element from this portion and swap it with A1. So the smallest is 23, so 23 and 38 will be swapped. Now in pass 3, we'll select the smallest from this portion and swap it with A2. So the smallest is 38, 38 and 59 will be swapped. So after pass 3, this much portion has become sorted. Now in pass 4, we'll select the smallest from this and swap it with A3. We can see the smallest is 45 and it is at its proper place. So no swapping is required in pass 4. Now in pass 5, we'll select the smallest from this one and swap it with A4. Smallest is 59. So 59 and 66 will be swapped. So after 5 passes, this much portion has become sorted and this is the largest element left. So after 5 passes, the whole array has become sorted. This is the method sort that will sort n elements of this array A using selection sort technique. And this is the method main, where we have called this method sort. Where we are entering the elements of the array, then we are sorting the array using this method, and then we are displaying the contents of the array. Now let's see this method sort. In this for loop, I goes from 0 to n minus 2. So it will have total n minus 1 iterations. And each iteration of this for loop will correspond to a pass of the selection sort. Now in each pass, we'll find the index of the smallest element. This variable min index denotes the index of the smallest element in each pass. So here in this loop, we are finding the value of min index. Now after finding the index of the smallest element is swapped with element ai. And the swapping is done only if I is not equal to min index. Which means that if smallest element is at its proper place, that is, if it is at ith position, then there is no need of swapping. Now let's understand this with the help of an example. In pass 1, I is 0 and min index is initialized with I. So min index is 0, A min index is 45. J is initialized with I plus 1, so J is 1. Now AJ is less than A min index. So min index is changed, it becomes 1. J is incremented. Now AJ is greater than A min index. So min index is not changed. J is incremented. Now AJ is less than A min index. So min index is changed. Now J is incremented. Now AJ is greater than A min index. So min index is not changed. Now again AJ is greater than A min index. So min index is not changed. And J stops here. So at the end of pass 1, we have got the index of the smallest element, which is 3. So we have to swap AI and A min index. So this 45 and 12, they are swapped. So at the end of pass 1, this portion becomes sorted. Similarly, other passes will proceed. In pass 2, I will be 1 and J will go from 2 to 5. In pass 3, I will be 2 and J will go from 3 to 5. In pass 4, I will be 3 and J will go from 4 to 5. In pass 5, I will be 4 and the value of J will be 5. Now let's run the program and see the output. So we get the sorted output. In pass 1 of selection sort, A min index is compared with elements from A1 to An minus 1. So we have total n minus 1 comparisons in pass 1. In pass 2, A min index is compared with elements from A2 to An minus 1. So we have total n minus 2 comparisons. Similarly, in pass 3, we have n minus 3 comparisons and so on. In the last pass, we have only one comparison. So the total number of comparisons in selection sort is equal to n minus 1 by 2, which is order of n square. Now selection sort is not a data sensitive sort, which means that the number of comparisons is the same in all the three cases, whether the input data is in sorted order or reverse sorted order or in random order. Now there is very less data movement. As we have seen, there is only one swap in a single pass, and that swap is also not required if the element is at its proper place. This is an in-place sort, which means the space complexity is order of 1. We have seen that only one single variable is required for swapping. Now this is an unstable sort, which means that it might change the relative order of the duplicate elements in the sorted output. Now let's understand with the help of an example why this selection sort is not a stable sort. This is an array of 7 elements and we have 3 duplicate elements in this. 24 is coming 3 times. Let's give a suffix to this 24 so that we can distinguish all the 3 24s. Now we'll sort this array using selection sort. The smallest element is 8, so first 8 will be swapped with 14. Next the smallest element is 10, so 10 will be swapped with this. Next the smallest is 14, so 14 will be swapped with this. Next the smallest is this, so it is at its proper place. Next the smallest is this, so it will be swapped with this. Next the smallest is this, so it will be swapped with this. Now the whole array is sorted and we can see that the order of these 3 24s has changed. Initially it was ABC, now you can see it is BAC. So this means that selection sort is not a stable sort. In this video we are going to discuss the bubble sort algorithm. In bubble sort, sorting is performed by comparing adjacent elements and swapping them if they are not in order. Let's see the whole procedure of this bubble sort algorithm. Suppose we have this array A of n elements and we have to sort it in ascending order using bubble sort. So in pass 1, first we will compare elements A0 and A1, and if A0 is greater than A1, we will swap them. Next, A1 and A2 will be compared, and if A1 is greater than A2, then they'll be swapped. Next, A2, A3 will be compared and swapping will be done if A2 is greater than A3. Similarly, other comparisons will be done and the last comparison will be between elements an-2 and an-1, and swapping will be done if an-2 is greater than an-1. Now at the end of pass 1, the biggest element of the array will come down at this n-1th position. Now in pass 2, again we'll start comparing from A0. So A0 and A1 will be compared and swapped if A0 is greater than A1. Next A1, A2 will be compared. Next A2, A3 and so on. And the last comparison this time will be between elements an-3 and an-2 because this is already sorted. So at the end of pass 2, the second largest element comes down at this position. So we can see that after 2 passes, this portion of the array has become sorted. Now in pass 3, again comparisons start from A0. A0, A1 are compared, then A1, A2 and so on. And this time the last comparison is in between an-4 and an-3. And swapping is done if an-4 is greater than an-3. So at the end of pass 3, the third largest element comes down at this place. And this procedure is continued till the last pass, which is the n-1th pass. And in that pass, there will be only one comparison, which will be between elements A0 and A1. And if A0 is greater than A1, swapping will be done. So after n-1 passes, this whole portion of the array becomes sorted. The element left is this A0, and this will definitely be the smallest element. So we can see that if our array has n elements, then after n-1 passes, the whole array becomes sorted. In the previous video, we saw the whole procedure of bubble sort algorithm. Now we'll take an example and see how this bubble sort works. This is an array of 6 elements and we are going to sort it in ascending order using bubble sort. And pass 1, first elements A0 and A1 are compared. You can see that this A0 is greater than A1, so we'll swap them. Next A1 and A2 are compared. There's no need of swapping since this is smaller. Next A2 and A3 are compared. Again there is no need of swapping. Next A3 and A4 are compared. Now this is bigger, so we'll swap them. Next A4 and A5 are compared. Again we need to swap, so we'll swap them. Now at the end of pass 1, we can see that the biggest element is 66. It has come down at the last position. Now in pass 2, again we'll start comparing from here. So here we don't need to swap. Here also we don't need to swap. Here we need to swap since 59 is greater than 38. So we'll swap them. Here also we need to swap. So we'll swap them. Now at the end of pass 2, the second largest element has come down at this 4th position. In pass 3, again we'll start our comparisons from this A0. A0, A1 are compared, no need of swapping. This and this are compared, we need to swap, so we'll swap. A2 and A3 are compared, we need to swap, so we'll swap them. Now at the end of pass 3, the third largest element has come down at this place and this much portion has become sorted. Now in pass 4, A0, A1 are compared, no need of swapping, A1 and A2 are compared. We need to swap since 38 is bigger, so we swap them. Now at the end of pass 4, this much portion has become sorted. Now in pass 5, this is the last pass. There is only one comparison, which is between A0 and A1, and we need to swap since A0 is greater than A1. So we'll swap them, and at the end of pass 5, this much portion has become sorted, and this is the smallest element. So we can say that the whole array has become sorted after 5 passes. This is the method sort that sorts n elements of this array A using bubble sort technique. And this is the method main, in which we are calling this method sort. Here we are entering the elements of the array. After that, we sort the array using this method, and then we print the sorted array. Now let's see the method sort. Here we have two nested for loops. In the outer for loop, we have a variable x that goes from n-2 to 0, where n is the number of elements. In this inner for loop, we have this variable j that goes from 0 to x. Now inside this inner for loop, we are comparing adjacent elements aj and aj plus 1. And we are swapping them if aj is greater than aj plus 1. And the swapping is done with the help of this variable temp. So now let's see how these nested loops work and sort our array. In this outer for loop, x goes from n-2 to 0. So it will have total n-1 iterations. And each iteration of this outer for loop will correspond to a pass of the bubble sort. For example, first iteration will correspond to first pass, second iteration will correspond to second pass, and so on. Now suppose we have to sort an array of 6 elements. So value of n will be 6. In the first iteration of this outer for loop, x will be equal to 6 minus 2. So x will be 4. In this inner for loop, j will go from 0 to 4. So this inner for loop will have total 5 iterations. In first iteration, j will be 0. So a0 and a1 will be compared. In second iteration, j will become 1. So a1 and a2 will be compared, and so on. And in the last iteration, j will become 4. So a4 and a5 will be compared. Now in the next iteration of this outer for loop, x will become 3. So j will go from 0 to 3. And this inner loop will have total 4 iterations. In first iteration, j will be 0. So a0 and a1 will be compared. In second iteration, j will be 1. So a1 and a2 will be compared, and so on. And in the last iteration, j will be 3. So a3 and a4 will be compared. Now similarly, other iterations of this outer for loop will proceed, and in the last iteration, x will be 0. So this inner for loop will have only one iteration this time, and value of j will be 0 in that last iteration. And so a0 and a1 will be compared. So in the last iteration of this outer for loop, which corresponds to last pass of the bubble sort, there will be only one comparison, and it is in between elements a0 and a1. Now let's understand this with the help of example that we have seen in the theory part. In pass 1, the value of x is 4 and j goes from 0 to 4, because the first comparison has to be done between a0 and a1, and the last comparison has to be done between a4 and a5. In pass 2, x is 3 and j goes from 0 to 3, because this time the last comparison has to be done between a3 and a4. In pass 3, x is 2 and j goes from 0 to 2, because this time the last comparison has to be done between a2 and a3. In pass 4, x is 1 and j goes from 0 to 1. In pass 5, x is 0 and j has only one value 0. There is only one iteration of the inner for loop, and in that iteration j is 0 and the elements a0 and a1 are compared. So this is the situation when the number of elements is 6. In pass 1, x is 4, j goes from 0 to 4, and these are the comparisons that are made. In pass 2, x is 3, j goes from 0 to 3, and these are the comparisons. So we can see that x goes from n-2 to 0 and j goes from 0 to x in each pass. Now let's run our program and see the output. So we get the sorted output. We can make an improvement in the bubble sort program that we have made. Let's see what that improvement is. We know that an array of n elements can be sorted in n minus 1 passes. Now it is possible that the array becomes sorted in less than n minus 1 passes. For example, if we have an array of 6 elements, it is possible that it becomes sorted after this pass 2 or after the pass 3 only. So there's no need of executing other passes. Let's see this with the help of an example. This is an array. In pass 1, we'll do all the comparison swappings that are required. And after pass 1, the array is this. After pass 1, the array has not become sorted. The whole array has not become sorted. We go to pass 2, we'll do all the comparisons and swappings whatever are required. And after pass 2, the array is this. So we can see that after pass 2 only, the whole array has become sorted. So now here in this example, we can see that the array has become sorted. But in the program, we need some way to detect that the array has become sorted. So what we can do is we can count the number of swaps in a pass. If the number of swaps in a pass is 0, it will mean that the array has become sorted. Let's see in this example only. In pass 1, we made 4 swaps. In pass 2, we made 1 swap. And in pass 3, there will be no swap because after pass 2 only the array became sorted, and when we'll do all the comparisons in pass 3 there will be no swaps. So whenever the number of swaps in a pass is 0, it will mean that the array has become sorted. Now let's see what modifications we have done in our program. We have taken a variable swaps that will denote the number of swaps done in a pass. At the starting of each pass, we initialize this variable to 0. And whenever in a pass we are performing a swap, we increment the value of this variable. At the end of each pass, we are checking the value of this variable. If it is 0, then we'll come out of this outer for loop. Because no swaps in a pass denotes that the array has become sorted. Now let's analyze the bubble sort algorithm that we have studied. A bubble sort is a data sensitive sort. That means the performance of the sort will depend on the order of the input data. It will have different performance when the data is in sorted order, or it is in reverse sorted order, or in random order. So let's see its performance in all these 3 cases. First, when data is in sorted order, there will be only one pass, because in first pass only there will be no swaps. So other passes will not be executed. The number of comparisons will be n minus 1, because in first pass the number of comparisons are n minus 1. So the total number of comparisons in this case will be n minus 1. There will be no swaps, as you know, and the time complexity in this case is order of n. Now when the data is in reverse sorted order, we'll have total n minus 1 passes, and the total number of comparisons will be this, because in first pass there will be n minus 1 comparisons, in second pass there will be n minus 2 comparisons, and so on, and in the last pass there will be only one comparison, and this total is n minus 1 by 2, which is order of n square. And the total number of swaps will be the same, because whenever we'll compare 2 adjacent elements, always we'll have to swap them, because the data is in reverse sorted order. So let's see the case when data is in random order. So we know that in first pass there are n minus 1 comparisons, in second pass there are n minus 2 comparisons. So in ith pass, the total number of comparisons is n minus I. Now suppose we need p passes in this case. So the total number of comparisons will be this, which totals to this. Now it can be shown that the number of passes in average case is order of n. So this becomes order of n square. So in this case also, the complexity of bubble sort is order of n square. In this video, we are going to discuss the insertion sort algorithm. Now in insertion sort, sorting is performed by inserting each element at its proper place in a sorted list. This sorting is based on a simple technique that is used by card players for arranging their cards. Now suppose a card player has these cards and he has arranged them in proper order. The new card that he receives is this, and he has to place this card among these cards that he has already arranged. So the process would be Now 10 is greater than 5, so 10 is moved this side. 9 is greater than 5, so 9 is moved this side. 7 is greater than 5, so 7 is moved this side. Now 2 is less than 5, so the proper place for 5 is found. 5 is inserted here. Now the new card is this. Now 10 is greater than 8, so 10 is moved this side. 9 is greater than 8, 9 is moved this side. Now 7 is less than 8, so proper place for 8 is this, so it is inserted here. So we can see that the technique is to place the new card at its proper place in the already sorted cards. Now let us see the whole procedure of the insertion sort algorithm. This is the array A of n elements that we are going to sort in ascending order using insertion sort. Now in insertion sort, we'll consider our array to be divided into two parts. One is the sorted part and one is the unsorted part. And in each pass, we'll take the first element from the unsorted part and place it at its proper position in the sorted part. So now in pass 1, our sorted part is this and unsorted part is this. And the first element of the unsorted part is this A1 and it is placed at its proper position in the sorted part. So the result of pass 1 is that this becomes the sorted part and this becomes the unsorted part. Now in pass 2, the first element from this unsorted part is inserted in this sorted part at its proper position. In pass 3, this is the sorted part and this is the unsorted part, and the first element is A3 and it is placed at its proper position and in this sorted part. This process continues till the last pass, which is the n-1th pass, and in this pass the element an-1 is inserted at its proper position in this sorted portion. So after n-1 passes, the whole array becomes sorted. We'll take an example and see how insertion sort works. Now this is an array of 8 elements and we'll sort it in ascending order using insertion sort. Now in pass 1, this is our sorted part and this is the unsorted part. And the first element of the unsorted part is 23 and it has to be placed in the sorted part. Now 45 is greater than 23, so 45 is moved this side and 23 is placed here. Now in pass 2, this becomes the sorted part and this is the unsorted part. And the first element from the unsorted part is 32. So now 45 is greater than 32, so 45 is moved this side. 23 is less than 32, so 32 is placed here. Now in pass 3, the first element from the unsorted part is 10 and it has to be placed in this sorted part. Now 45 is greater than 10, so 45 is moved this side. 32 is greater than 10, 32 is moved this side. 23 is also greater than 10, so it is also moved this side and 10 is placed here. Now in pass 4, this is the unsorted part and this is the first element of unsorted part. It has to be placed in this portion. Now 45 is greater than 30, it is moved this side. 32 is greater than 30, it is moved this side. Now 23 is less than 30, so we'll stop and place 30 here. Now in pass 5, 12 has to be placed in this sorted part. So 45 is greater than 12, it is moved. 32 is greater, it is moved. 30 is greater, it is moved. 23 is greater, it is moved. Now 10 is less than 12, so we'll stop and place 12 here. Now in pass 6, 66 has to be placed in the sorted part. Now 45 is less than 66, so we need not move anything and we go to pass 7. In pass 7, 28 has to be inserted in this portion. So 66 is greater than 28, so 66 is moved here. 45 is greater than 28, it is moved here. 32 is greater, it is moved. 30 is greater, it is moved. Now 23 is smaller, so we'll stop and insert it here. So after 7 passes, the whole array has become sorted. This is the method sort that will sort n elements of this array A using insertion sort. And this is the method main, where we have called this method sort, where we are entering the elements of the array, then we are sorting that array using this method, and then we are displaying the contents of the array. Now let's see this method sort. In this for loop, I goes from 1 to n-1. So this loop will have total n-1 iterations, and each iteration will correspond to a pass of the insertion sort. Now in each iteration, the elements from 0 to I minus 1 will form the sorted part, and the elements from I to n minus 1 will form the unsorted part. And this element AI will be the first element of the unsorted part, and it has to be inserted at its proper position in each pass. We have saved this element AI in this variable temp. Now in this inner for loop, the sorted part is scanned to find proper place for this temp, and this scanning begins from the end of the sorted part. We know that our sorted part is from 0 to I minus 1. So this j is initialized with I minus 1, and it is decremented each time. Now this loop executes till aj is greater than temp. Whenever we will find an element aj that is less than or equal to temp, this loop will stop. This statement aj plus 1 is equal to aj shifts the elements to the right. This condition j is greater than equal to 0 we have put to stop the loop in the case when temp is the smallest element of the array, and it has to be placed at index 0. Now when this loop stops, this temp is placed at the j plus 1th position of the array. Now let's understand this with the help of an example. We are sorting this array and we have finished 4 passes. We have to execute 5th pass. Now in 5th pass, I is 5. We can see that this sorted part is from 0 to I minus 1, and this unsorted part is from I to n minus 1. And this AI is the first element of the unsorted part. It has to be placed in this sorted part. Now j is initialized with I minus 1. So j is 4. Now aj is greater than temp. So the inner loop will execute, and this 45 will be shifted to the right using this statement. Now j will be decremented. It becomes 3. Now again aj is greater than temp. So this loop will execute, and this 32 will be shifted to the right. Now j is decremented. It becomes 2. Again aj is greater than temp. So the inner loop executes, and this 30 is shifted to the right using this statement. Now j becomes 1. Again aj is greater than 12. So inner loop executes, and 23 is shifted to the right. Now j becomes 0. Now aj is less than temp. So inner loop will stop, and temp will be placed at the j plus 1th position of the array. So this 12 will be placed here. And now this becomes a sorted part. Now let us run our program and see the output. So we get the sorted output. In this video, we'll discuss the analysis of insertion sort. Now the outer for loop will always have n minus 1 iterations, and the iterations of the inner loop will depend upon the order of the data. It can have 0 to I iterations. Minimum it can have 0 iterations, and maximum it can have I iterations. In each iteration of the outer for loop, the element AI has to be placed in any of these I plus 1 locations. Now if I is the correct place for the element AI, there will be only one comparison and no moves. If it has to be placed at index I minus 1, there will be 2 comparisons and 1 move. If it has to be placed at index I minus 2, there will be 3 comparisons and 2 moves. Now if it has to be placed at index 2, the number of comparisons will be I minus 1 and number of moves will be I minus 2. If it has to be placed at index 1, the number of comparisons will be I and moves will be I minus 1. If it has to be placed at index 0, comparisons will be I and moves also will be I. And in each case, we'll have 2 moves for loading and unloading the variable temp. So we have seen what happens in each iteration of the outer for loop. Now let's see how many comparisons and moves will be performed in all the 3 cases: when the data is in sorted order, when the data is in reverse sorted order, and when the data is in random order. So first let's take the case when data is in sorted order. In that case, in each iteration of outer for loop, AI will always be in its correct place. And we have seen that in this case, there is only one comparison and two moves. These two moves are for loading and unloading the variable temp. And the total number of comparisons will be n minus 1 and total moves will be 2n minus 1, since the outer loop has total n minus 1 iterations. And so in this case, the performance is order of n. Now let us take the case when data is in reverse sorted order. Now in this case, AI will always be less than all the elements from A0 to AI minus 1. So it will always have to be placed at index 0. And we have seen that when an element has to be placed at index 0, there are total I comparisons and I plus 2 moves. So the total number of comparisons in this case will be this. Since the outer loop has n minus 1 iterations, this comes out to be n minus 1 by 2, which is order of n square. And the total number of moves will be this, which is also order of n square. Let's find out the number of comparisons and moves that have to be performed when data is in random order. In this case, we assume equal probability of occupying all array locations. So average comparisons in ith iteration of outer for loop will be this much. We have seen that AI could be placed in I plus 1 locations and the number of comparisons in each case were this. So the average comparisons come out to be this much. Now average moves in ith iteration of outer for loop will be this much. So the total number of comparisons, we have performed summation from 1 to n minus 1, since the outer for loop has n minus 1 iterations. This comes out to be order of n square, and the total number of moves also comes out to be order of n square. So the performance of insertion sort in the case when data is in random order is also order of n square. Now insertion sort is a stable sort, which means that it maintains the relative order of the duplicate elements in the sorted output. It is an in-place sort, which means that the space complexity is order of 1. We don't require any extra memory for performing this sort. Now this sorting is efficient when n is small, because when n is small, the difference between order of n square and order of n log n is very less. So this sorting technique is good when the number of elements to be sorted is very less. Now one disadvantage of this sorting is that there are many movements. Now this can be costly if the elements that are being sorted are very large. Now this sorting is good for lists that are almost sorted, because in that case the number of movements will be very less. In this video we'll discuss shell sort. Now this sorting technique was given by Donald L. Shell in 1959, and this is an improved version of insertion sort. This is also known as diminishing increment sort. Now first we'll see the whole procedure of this sort, and then we'll see why it is an improvement over insertion sort. Now in this sorting technique, in each pass we'll take a number h called increment and we'll decrease it till the last pass, and in the last pass it should always be 1. In each pass we'll make h sublists, and each sublist is created by taking elements that are at a distance of h from each other, and these sublists will be sorted using insertion sort. Now suppose we have this array of 17 elements that has to be sorted using shell sort. The value of increments that we have taken are 5, 3 and 1. So we'll have 3 passes. In first pass increment will be 5, in second pass increment will be 3, and in third pass increment will be 1. Now in pass 1 increment is 5, so we'll make 5 sublists. The sublist 1 is this. It starts from A0 and all the elements are at a distance of 5 from each other. Sublist 2 is this. The first element is A1, and again all elements are at a distance of 5 from each other. This is sublist 3, starts from A2. This is sublist 4, and this is sublist 5. Now all these sublists are sorted using insertion sort. In pass 2 increment is 3, so we'll make 3 sublists. Sublist 1 is this, starts from A0 and all the elements are at a distance of 3 from each other. Sublist 2 is this, starts from A1. Again, all the elements are at a distance of 3 from each other, and this is sublist 3. These sublists are sorted using insertion sort. Now in pass 3, increment is 1, so we'll make only one sublist and that will contain all the elements of the array. Now this sublist will be sorted using insertion sort. So after the last pass, we'll get a sorted array. This is an array of 17 elements and we'll sort it in ascending order using shell sort. The value of increments that we'll take are 5, 3 and 1. So we'll have 3 passes. In pass 1, increment is 5. So we'll make 5 sublists. Now this is sublist 1. It starts from A0 and all the elements are at a distance of 5 from each other. Now this sublist will be sorted using insertion sort. So we'll get 11, 13, 21 and 48. Next sublist is this. After sorting it, we'll get 1, 3, 59 and 60. Next sublist is this. We'll get 2, 5 and 19. Next sublist is this. Sublist 5 is this. After sorting it, we'll get 4, 8 and 16. So after pass 1, we get a 5 sorted list. Means all the elements that are at a distance of 5 from each other in this list are sorted. Now in pass 2, value of increment is 3. So we'll make 3 sublists. Sublist 1 is this. It will be sorted using insertion sort. Sublist 2 is this. It starts from A1 and all the elements are a distance of 3 from each other. After sorting, it will be this. Sublist 3 is this. It starts from A2. All elements are at a distance of 3 from each other. After sorting, it will become this. So after pass 2, we get a 3 sorted list, which means that all the elements that are a distance of 3 from each other are sorted. If we compare this with the initial array, we can see that most of the elements have moved to their final places. So now we have a list that is almost sorted. Now in pass 3, increment is 1, so we'll make only one sublist and that will contain all the elements of the array, and this will be sorted using insertion sort. So after 3 passes, the whole list becomes sorted. This is the method sort that will sort n elements of this array A using shell sort. And this is the method main, where we have called this method sort. Here we are entering the elements of the array A. Then we are sorting this array using this method, and then we are displaying the sorted array. Now let's see this method sort. Here we are entering the maximum increment value. That is the increment value which will be used in the first pass. Now each iteration of this while loop corresponds to a pass of the shell sort. This loop executes till h is greater than or equal to 1. In each iteration, we are decrementing h by 2. That's why we have taken initial increment value to be an odd value, because otherwise this h will not become 1 in the last iteration of the while loop. And we know that in the last pass of shell sort, the value of h should be 1. So that's why we have taken this increment to be an odd value. Now let's see what happens in this while loop. Now this code is almost similar to that of insertion sort. There are some differences. Let's see what those differences are. There we had I equal to 1. Here we have I equal to h. There we had j equal to I minus 1. Here we have j equal to I minus h. There we had j equal to j minus 1. Here we have j equal to j minus h. And there we had aj plus 1 in these two places. And here we have aj plus h. Now in the last iteration of this while loop, h will be 1. And so this code will be exactly similar to that of insertion sort code. And so insertion sort will be performed on the whole list in the last iteration of this while loop. Now let's see what happens in other iterations of this while loop. Suppose in an iteration, value of h is 3. So in this for loop, I will be going from 3 to n minus 1. And so all the elements from A3 to An minus 1 will be inserted in their respective sublists one by one. Now suppose in an iteration, I is equal to 15 and we are inserting element A15. So in that case, in this for loop,
j will be initialized with 12. 15 minus 3. And in each iteration of this loop, j will be decremented by 3. Let's see this in a slide.
I is 15, so this element A15 has to be inserted in its sublist. Now in the inner for loop, j is initialized with I minus h. I is 15, h is 3, so j is initialized with 12. And each time j is decremented by 3. So j goes 3 positions backwards each time, and this is how we access the elements of this sublist. And whenever the elements have to move right, they have to move 3 positions. So that's why we have written aj plus h is equal to aj in our code.
So this statement aj plus h is equal to aj moves the elements h positions to the right. And at the end, this temp is inserted at j plus h index of the array. So this is how this while loop works. Now let's run this program. So this gives us the sorted output.
In shell sort, the running time depends on the number of increments and their values. Now the mathematical analysis of this sorting technique is very complex. Based on empirical studies, the performance was found out to be this for one set of increments and this for another set of increments. Now this is an unstable sort, which means that it might change the relative order of duplicate elements in the sorted output. This is an in-place sort, which means that space complexity is order of 1 and no extra memory is required for performing this sort. Now let's see why shell sort is an improved version of insertion sort. Now in insertion sort, we know that there are many movements, and the reason for many movements is that elements are moved only one position at a time. While in shell sort, elements can move long distances at a time. So if an element is far away from its final place, in insertion sort, it will have to go one by one, while in shell sort, it can jump and go to its final place. We know that insertion sort is efficient when the size of list is small and when the list is almost sorted. These 2 points are the basis of shell sort. In shell sort, when initially the increment is large, size of sublists is small, so insertion sort on those sublists is efficient. When in the final passes, increment becomes small, the size of sublist increases, but then also the insertion sort is efficient on the sublists because those sublists are almost sorted. Now let's talk about increments. The value of increments that we have taken in our example are 5, 3 and 1. Now we can take any other sequence of increments. The only condition is that the increment should decrease in every pass, and in the last pass the value of increment should be 1. Now the sequence of increments given by Donald L. Shell was this. We suggested to take first increment as half the size of list and then divide the increment value by 2 in each pass. So if we have 17 elements, then the value of increments would be this. We'll have 4 passes and the sublist form would be this. These are the subscripts of the elements. So we can see that in this case, the elements at odd positions and the elements at even positions are not compared until the last pass. They are compared only in the last pass. So this choice of increments is not a good one. In general, we can say that increments which are a multiple of each other, like 1, 3, 6, 9 or 1, 2, 4, 8, are not a good choice, because in these cases the same elements are compared in each pass. Increments which are relatively prime are a good choice. Now a sequence of increments given by Knuth is this: h1 is equal to 1, hi plus 1 is equal to 3 hi plus 1, and stop at hi when hi is greater than n minus 1 by 9. So if we have number of elements is 10,000, then the increments would be this.